All right, let's take a look at sketching a rational function where the degree of the denominator is 1 higher than the degree of the numerator. So here we have f of x is equal to x minus 3 over x squared minus 5x minus 14. We want to sketch this function with attention to domain and range, asymptotes, intercepts, and end behavior. So the first thing we want to do here, let's simplify this function. Let's use a different color. Let's simplify this function. F of x is equal to x minus 3. I'm going to factor out the denominator. So this is factorable. On two numbers that add up to -5 that multiply to -14, you could do x minus 7 and x plus 2. Okay, so that's its factored form, and then you can really clearly tell what the restrictions on the domain is. So domain, x belongs to a set of all real numbers. X cannot equal 7 or -2. Okay. Now, if we're looking at a range here, we know that if the degree of the denominator is 1 higher than the numerator, then y belongs to all real numbers, but y cannot equal 0, right? So the restriction is going to be 0. However, we state that there are going to be potential exceptions here, right? Because although y cannot equal 0, an x-intercept will exist. Okay, so an x-intercept will exist, so this is the exception. So we need to kind of consider these exceptions when we're considering these functions, right? So let's take a look at some of the asymptotes here. Okay, so for part B, the vertical asymptote here, x is equal to 7 and -2. The horizontal asymptote should be y is equal to 0, but for the most part, our x-intercepts will exist. Let's take a look at our intercepts. Right, so our x-intercept here is going to be, I'm going to let f of x equal 0. So if I let f of x equal 0, I get x minus 3 over x squared minus 5x minus 14 is equal to 0. In this case, x is equal x minus 3. So we're looking at the numerator to find the x-intercept. So x is equal to 3. So 3 and 0 is our x-intercept. Okay, so we can also find our y-intercept here. So if I want to find my y-intercept, what I'm going to do here is I'm going to let x equal 0. You're doing f of 0 here is equal to 0 minus 3 over 0 squared minus 5 times 0 minus 14. So we get -3 over -14 cancels out. Right, so f of 0 is about 3 over 14. So it's slightly less than 1 here. Okay, so now we're going to create our sketch, right? So I'm just going to insert my grid here. Alright, so here's my grid, and what I want to do here is let's place our vertical asymptotes. I'm going to do the vertical asymptote in red. Alright, my vertical asymptote here is 7 and -2, so my -2, let's say we have it here. So guys, try to use a ruler for this. Okay, so this is my vertical asymptote, -2, whoops. Okay, this is one of the reasons why I tell you guys to use a ruler. Anyways, vertical asymptote, x is equal to -2. The horizontal, we also have another vertical asymptote, 7, so this is 3, this is 4, so this is 7, right? So we have a vertical asymptote at x is equal to 7. Okay, and we also have a horizontal asymptote at y is equal to 0. Okay, so that's our horizontal asymptote, and we can plot some of our intercepts. So when I'm plotting some of my intercepts, I have an x-intercept at 3 and 0, so let's put that right there. So this is 3 and 0, right? And we also have a y-intercept at 3 over 14, right? So let's say it's somewhere here. So it's like, right, so this is 0 and 3 over 14, okay? And now what we want to do here is we want to create a sketch. Now because we have an x-intercept, we can understand that the graph is going to go through that x-intercept. And how you can determine some of the behaviors of this function, I'm going to do some test points, right? So my function, f of x is equal to x minus 3 over x minus 7 x plus 2. Now I'm going to take a look at a point that's close to one of the vertical asymptotes. So this is the -2, and this is x is equal to 7. So this is the other vertical asymptote, right? So let's take a look at a value that's close to this vertical asymptote. Let's take a look at f of -1, right? So if I do f of -1 here, I get -1 minus 3 over negative 1 minus 7 times negative 1 plus 2, which is negative 4 over negative 8 times 1. So this cancels out, so you get 1/2, right? So negative 1 and 1/2, so it's going to be slightly up here. Okay, so this is negative 1 and 1/2, so you can see that gets bigger and bigger, right? But let's take a look at let's take a look at f of something really close to 2. Let's do f of 1.9. So we get negative 1.9 minus 3, negative 1.9 minus 7, negative 1.9 plus 2. So this is going to give us negative 4.9 over negative 8.9 times, what is this? Let's say that's going to be negative 0.1, right? So this is going to cancel out. No, sorry, positive 0.1. Okay, so this is positive 0.1, right? So it cancels out. This is 0.89, so 4.9 divided by 0.89, that's going to give us 5.51. Okay, so this actually, the value gets higher and higher, right? So the closer it gets to this asymptote, the x value will actually approach positive infinity. So 1, 2, 3, 4, 5. Let's say it's like somewhere here, right? So it's going to get closer and closer to that point. Right, so I'll get closer and closer to that point. So technically what's going to happen here, if I did draw my sketch, right? So the point gets closer and closer, gets closer and closer to our asymptote. Okay, so it gets closer and closer to our asymptote, right? And what's going to happen here is it's going to go through this point, right? Now we need to figure out what's the behavior. Is it going to go back up like a parabola, or is it going to go back down? Well, let's test some points here. So if we test some points, let's test f of something close to this asymptote. Let's do f of 6.5. So if you do f of 6.5, you plug this in, you get 6.5 minus 3, right? And then you're going to get 6.5 minus 7 times 6.5 plus 2, and then you get 6.5 minus 3, which is, to clean this up here, right? 6.5 minus 3 is going to give us 3.5 over negative 0.5 times 8.5. Okay, so if we crunch that out, 3.5 divided by 0.5 times, or negative 0.5 times 8.5, we're actually going to get negative 0.824. So you're going to actually see that it's going to get more and more negative. Yeah, so it's going to get more and more negative, right? So it's going to be somewhere like right there. Right, so because of that, it's going to actually cross through the point. You can actually, if you keep doing some test points, right? If you do some test points, you actually see that the sketch will look like that. So it's actually going to be a sigmoid. So this is where the exceptions will take place. And if you guys do some more test points, if you do f of 8, for instance, right, you would see it's positive, and it actually follows the confines of the asymptote. So you guys can do some test points, but once again, we just want to create a sketch, right? And if you do f of negative 2, you plug this in, you're also going to see that the values would be positive. Right? Sorry, x can't be negative. F of negative 3, for instance, right? You're going to see that it's going to be, is it going to be negative or positive? Let's just test it. Right, so if you do f of, let's do negative 3. So f of negative 3. So we just want an idea of what the graph is going to look like. Negative 3 minus 3, negative 3 minus 7, negative 3 plus 2. So this is negative 6 over negative 10 times negative 1. Right, so this is actually going to be negative. So because it's negative, then the sketch is actually going to look like this. Right, it's going to actually follow the confines of the graph. So you guys can keep doing test points, but this is what the graph will essentially look like, right? So by doing test points, you guys can kind of figure out what the sketch will look like, right? So it's somewhat irregular, right? Like I can do another point like negative 6 here, right? If I plug in negative 6, you get negative 6 minus 3, negative 6 minus 7, negative 6 plus 2, which is negative 9, negative 13, negative 4. So you're going to see that's very small and smaller negative, right? So that's why, yeah, it's a very irregular sketch, right? So that's what we're going to be seeing there. And just by looking at the sketch, we can also look at the end behavior, right? So let's do the end behaviors right here. So if I'm looking at the end behavior, as x approaches negative infinity, as I'm going this way on the graph, y will approach the horizontal asymptote 0 from below. As x approaches the vertical asymptote, in this case is -2 from the left-hand side, right, y will approach negative infinity as x approaches -2 from the right-hand side. So I'm going this way, right? Y is approaching, if you follow the orange trace, y approaches positive infinity as x approaches the next vertical asymptote, which is 7 from the left side, right? Y basically will approach negative infinity, and as x approaches 7 from the right hand side, y approaches positive infinity, and as x approaches positive infinity, y is going to approach, it's going to approach the x-axis, it's going to approach 0 from up top. Okay, so those are the end behaviors of our function. So it's somewhat quite irregular, but once again, we can kind of use some of these principles to help